Welcome to Math World. Today's class I'm going to discuss some properties of argument of Z. We know how to find argument of Z, right? If Z is written in Cartesian form or even in exponential form, or even in polar form, right? We know how to find argument of Z. We even know how to find principal value of argument of Z, that's arg Z, which is nothing but tan inverse of y by x if both x and y are positive, and it's minus tan inverse of y by x if x is positive and y is negative, then it is pi minus tan inverse of y by x if x is negative and y is positive, and it is minus of pi minus tan inverse of y by x if x and y both are negative. And we also know if x is 0, in the sense if y by x is infinity, in that case argument of z is simply pi by 2 if x is 0 and y is positive. This is minus pi by 2 when x is 0 and y is negative. In that case, when you take tan inverse of y by x, it's infinity. Okay, and we also know one more thing. If z is a negative real number, then argument of z is nothing but pi. If z is a negative real number, then principal argument of z is pi, and if suppose z is a 0, if z is 0, then argument of z is not defined or undefined for z equal to 0. This is a basic that we know, right? I'll take up one few examples just to find out the principal value of argument of z. What happens if x, y are positive or negative, like that? Okay, so let us take z equal to 1 plus I. Here x is 1, y is 1, right? So argument of z is nothing but simply tan inverse of y by x, that's 1 by 1, so I can directly write it as pi by 4. If y is negative, that's say 1 minus I, z is 1 minus I, then we know when y is negative, and x is positive, it's minus tan inverse of y by x, so it's minus tan inverse of 1 by 1, so it's minus theta, which is nothing but minus pi by 4. Similarly, what happens if x is negative? That's say z equal to minus 1 plus I. Now argument of z is nothing but 180 minus theta, that's pi minus tan inverse of 1 by 1, so it's pi minus pi by 4, so it's 3 pi by 4. Okay, and when both x and y are negative, that's minus 1 minus I. So in that case argument of z is nothing but minus of pi minus theta, that's tan inverse of 1 by 1, so it's minus of pi minus pi by 4, which will be minus 3 pi by 4. Okay, so here these are the cases where I'm taking different signs of x and y. Now what happens to argument of z when I have multiplied two complex numbers? Say I have z1 equal to, if z1 equal to say r1 e power I theta 1 and z2 equal to r2 e power I theta 2. Then it says we know z1 into z2 will be equal to r1 into r2 into e power I theta 1 plus theta 2. This we know, right? So now the thing is, what happens to argument of z1 z2? Says argument of z1 z2 will be equal to argument of z1 plus argument of z2, and similarly argument of z1 by z2 equal to argument of z1 minus argument of z2. See, when we have suppose z1 is here, okay, which makes an angle theta 1, and z2 is somewhere here, which makes an angle theta 2. Then z1 z2 will be somewhere here, okay, which makes an angle theta 1 plus theta 2, right? That we know. This angle is theta 1 plus theta 2. So when we are writing argument of z1 z2, argument of z1 into z2, we can even write it as theta 1 plus theta 2 plus 2n pi, where n can be any value, right, depending on the rotation, which direction you are giving and how many times you are rotating, right? So that gives argument of z1 z2. In fact, see, if you want to prove it theoretically, say suppose we know z1 is r1 e power I theta 1, so I can even write it as z1 equal to r1 into cos theta 1 plus I sin theta 1, right? And z2 I can write it as r2 into cos theta 2 plus I sin theta 2. Now z1 z2 is nothing but r1 cos theta 1 plus I sin theta 1 into r2 into cos theta 2 plus I sin theta 2, right? So r1 r2 will write together, then cos theta 1 into cos theta 2 minus, because I square is negative, so cos theta 1 cos theta 2 minus sin theta 1 sin theta 2, that will become cos of theta 1 plus theta 2, then cos theta 1 sin theta 2 plus sin theta 1 into cos theta 2 whole together with I. So that comes out to be sine of a plus b, that's sin theta 1 plus theta 2. So I'm directly writing this, okay, cos of theta 1 plus theta 2 plus I into sine of theta 1 plus theta 2. So this is nothing but you can even write r1 r2 into cis theta 1 plus theta 2. This is z1 z2. So when I have written like this, argument of z1 z2, we can write it as theta 1 plus theta 2 plus 2n pi. Right, that this we always write when we are writing argument of z1 z2. But when we are taking a principal value, we are taking particular n value and we are writing angle. Okay, so now see argument of z1, if I simply take, I'm not writing directly simply theta 1, right? I'll write theta 1 plus 2, say 2n1 pi. Some particular value of n I'm taking and I'm writing the argument of z1. So when I have written like this, theta 1 plus theta 2 plus 2n pi, this part I can write it as theta 1 plus theta 2 plus 2 into n minus n1 pi, which is extra that I'm removing. Okay, so I can write this with theta 1 plus theta 2 plus 2n pi. No, I'm writing theta 1 with respect to particular value of n. So theta 1 plus 2n1 pi, but this is extra I'm taking, no? So that I'm removing 2n1 pi. Okay, so this is what happens when you are taking argument of z1 z2, which is nothing but argument of z1 plus argument of z2. If you are writing argument values, we are writing depending on the rotation, so we are adding 2n pi plus for that, but it's simply argument of z1 z2, sorry, z1 plus argument of z2. Okay, now the thing is, what happens when I consider z1 by z2? That's argument of z1 by z2. Okay, this is same as writing argument of z1 into z2 inverse. So depending on this, I'm rewriting this as argument of z1 plus argument of z2 inverse. Argument of z1 plus argument of z2 inverse is nothing but z2 inverse, no? So it's 1 by r2 into e power minus I theta 2. Z2 is r1 e power I theta. When you take its inverse, e power minus I theta. Okay, so it's minus I theta 2. So this is same as writing argument of z1 minus argument of z2, because e power I theta 2, so it's minus of argument of z2. See, this is true when I'm taking argument of z, but what happens if I take particular argument, that's in the sense principal argument? Is it true when I take principal value of argument of z, that is arg z? So these two may not work, in fact, when I take a principal value of argument of z. Okay, say for example, if I have z1 as I and z2 as minus 1. Okay, now what is z1 z2? It's minus I. Now let us take argument z1, that is pi by 2. And similarly argument of z2 2, that's minus 1, so it's a negative real number, so our principal value is pi. Now argument of z1 z2, that's argument of minus I, which is nothing but tan inverse of 0 by minus 1, so it's minus pi by 2. Now you check with this. We know this argument of z1 z2 is nothing but argument of z1 plus argument of z2. But when you take principal value, say this is pi by 2 plus pi, it's 3 pi by 2, which is not equal to minus pi by 2. So if you consider principal argument of z, then this may not work. For few examples it works, but not for all. But see, this is not working for this, but when I take say argument of z1 by z2, no? In that case, it's argument of z1 minus argument of z2, no? Even if I take a principal value, that's pi by 2 minus pi, that gives me minus pi by 2. So it works. This works when I take a principal argument, but this won't work when I take a principal value of argument of z. So for this example in particular, this won't hold, but this holds. But if you take a general argument of z, then it works. Okay. There are many such examples where when you consider a principal argument of z, these two may not work, but for few it works. Okay. Now let us move forward. Now we know that mod z equal to r is written as, say, z equal to r e power I theta, where theta lies between 0 and 2 pi. This represents a circle having counterclockwise rotation of radius r and center at the origin, right? So I can even write mod z minus z naught equal to r, where z is z naught plus r e power I theta, and again theta lies between 0 to 2 pi. If I write like this, then this also represents a circle whose radius is r but center at z naught, right? So we know this concept. Now let us take one problem depending on this. When I have a complex number which is written like mod z equal to r, then it can be represented or it can be expressed as z equal to r into 1 plus it divided by 1 minus it. Every complex number on the circle mod z equal to r can be expressed as r into 1 plus it divided by 1 minus it, where r is greater than 0 and t belongs to r. See, every complex number on the circle mod z equal to r can be written as z equal to r e power I theta, right, in the polar form. Where theta lies between, say, now say I'm writing it in exponential form. Now this I theta, I can even rewrite it as e power I into theta by 2 plus theta by 2, right? So when I have written like this, I can rewrite this e power I theta by 2, and 1 I theta by 2, I'm taking it down like this, e power minus I theta by 2. Is it okay? Now this I can write it as e power I theta by 2 can be written as cos theta by 2 plus I sin theta by 2 divided by, this is cos of minus theta by 2 plus I sin of minus theta by 2. So it's same as writing cos of minus theta is cos theta I sine theta by 2 divided by cos of theta by 2 minus I sine of theta by 2. When I divide this whole by cos theta by 2, then this comes out to be r into cos theta by 2 cos theta by 2, that is 1 plus I sine theta by 2 divided by cos theta by 2. So that will be tan theta by 2. Similarly over here 1 minus I tan theta by 2. If I take t equal to tan theta by 2, then this will be r into 1 plus I t divided by 1 minus I t, where t is nothing but tan theta by 2. I hope it is clear. I'm dividing this whole by cos theta by 2. Both numerator and denominator is divided by cos theta by 2, so that cos theta by 2 by cos theta by 2 will become 1, and sin theta by 2 cos theta by 2 is tan theta by 2, like that. Okay, so this is about argument of z, and when z is represented as a circle, when z represents a circle, then it can be expressed in this form: r into 1 plus it divided by 1 minus it. In my next video, I'm going to discuss roots and powers of a complex number. Thank you for watching.